My name is Qichen. I'm from Seoul National University of South Korea. And today I'm going to talk about operating system I/O path optimization for especially flash solid-state drives. And this is a joint work with my colleagues at Seoul National University. Okay, so now these days we are looking at new non-volatile memory technologies which are a lot faster than magnetic disks. They boost the performance of storage devices, showing remarkable performance numbers. However, once we get these technologies online, we soon notice a different performance number at the application level, which is much less. And this is because there are certain costs of software to perform I/O going through the operating system. And for Linux, for example, it is reported that an I/O request going through the I/O path spends something around 13 microseconds, which can be excessive when accessing a NVMe-based storage device, which is in single-digit microseconds. And this problem was well studied and has been discussed during about 2010 and 2011, and there was research about resolving the situation. And with various techniques, the research was focusing on simplifying the I/O path, reducing the computational distance between the application and the storage device. And among all those techniques, one interesting optimization was the poll, about reducing context switches by having the issue thread, holding the CPU, busy waiting until the device finishes the work. And this was particularly efficient because the access latency of the underlying device was under about 10 microseconds, like 4 or 5, assuming the use of PCM or even DRAM for prototypical research platforms. And in this case, yielding the CPU would introduce unnecessary overheads, as explained in the previous talk. So previous studies regarding these optimizations, such as Monada-D from UCSD, led to a reduction of software latency all the way down to 1 microsecond or less, and it was really remarkable. But, okay, what about flash SSDs? Can we apply all these techniques to the current generation of flash SSDs? Since flash SSDs need at least 50 microseconds and 100 microseconds for normal MLC SSDs to perform in an I/O, the picture is slightly different. Okay, so first, if we simplify the I/O path, getting rid of the 13 microseconds, as I said before, it won't be that much dramatic, but it is beneficial. So this is the right way to go. But what about poll? Since flash SSDs have longer and unpredictable latencies, reducing context switches using poll would waste CPU cycles and lower device utilization. So for flash, we have to stick to the conventional interrupt-based completion path, but this comes at a cost of multiple context switches and between multiple I/O processing contexts, which can cause unpredictable delays. And this is bad. But how bad is it? How many context switches are there? And why do we even have them? Well, operating system 101, there is the first context switch where the thread issues an I/O and sleeps. And this is because we don't want to make the thread waste CPU cycles waiting for the device. And here, we rely on a context triggered by the device to wake the thread up, and it's the hardware interrupt. And if we have hardware interrupts, since we can lock up the system, we expect the software interrupt handler, which defies the I/O processing, to offload the main hardware interrupt. And this way we can avoid system lockups when I/O is going crazy, high rates. And this basically introduces at least 2 context switches in the completion path. But is this all? Devil lives in the details, and Linux, for example, interrupts are steered to enhance the CPU cache utilization of I/O processing, thus improving system throughput. And this is actually implemented using an IPI call, and this introduces another context switch. And yet another, there is also a background kernel thread which issues due requests which could not be previously issued because the device was busy. This actually runs the queue. And all of these context switches, several context switches build up in the completion path, which can result in a much larger, unpredictable, unbound delay compared to the 13 microseconds, especially in a busy CPU. So the question we asked ourselves was, how can we minimize the number of context switches without introducing side effects such as system lockups or poor cache utilizations? And something like the figure on the right. So in this work, we did this by performing a set of optimization based on a new hardware interface implemented as a HAL. And for the interest of time, I will go only over the key optimization, which is underlined. And please read the paper for the other optimization for the more details. Okay? So for the first optimization, the first thing we did was eliminating the additional context, such as the background queue runs and the deferred I/O processing context, the software IRQ handler, and the IPI. The relevant I/O processing tasks were relocated to the hardware interrupt, and this was possible because all I/O operations were implemented in a non-blocking manner. The benefit of doing this was the elimination of the additional context we saw previously, and another benefit was the minimization of device I/O slot idleness. As soon as an I/O queue handler frees up an I/O slot, a new I/O request can be issued right away without the delay of waking up a thread. But, okay, yes, this is counterintuitive, and this makes the hardware interrupt even more heavier. And we're going to deal with it with the next two optimizations. So for the offload, we introduced some schemes. Here, instead of introducing a new context, we did it in a different way. We decided to use the completion context of the user thread, which is waiting for an I/O to complete. This is the very context where the result of a read system call or a write system call is waited for. Here, the post-processing stage is split in a half. So the first half, which is placed on the IRQ handler, frees up the device from the I/O request and wakes up the corresponding completion context, the waiting thread. Whereas on the other half, which is placed on the completion context, post-processes the rest and goes back to the completion context without any context switches because it's already there. And here, additionally, we try to maximize cache hits by using CPU affinity mask instead of introducing IPIs. CPU affinity masks are limited to the current CPU before an I/O is being issued and the issue thread is going to sleep. And this prevents the I/O thread from being scheduled on another CPU when waking up. It just wakes up on the same CPU. And the interrupt, then the CPU mask is restored as it was before. And with all of this, in effect, we are offloading the hardware interrupt handler without introducing any new context switches. But this still has some problems because the hardware interrupt has to do some more. So we went a little bit more further to offload the hardware interrupt handler. And we did this by introducing cooperative context embedded in both issue and completion sides of the I/O threads. And here, cooperative contexts perform pretty much the same thing which the hardware interrupt handler actually does. They look into the implicit completion queue and the issue queues to steal the work which the hardware interrupt otherwise has to perform. And the work includes the pre-post processing stage, waking up corresponding context of completed I/O requests, and the task of issuing new ones. And since these cooperative contexts are embedded in all issue and completion side contexts, now we have an abundant parallel I/O processing context throughout the system without introducing unnecessary context switches. And this significantly reduces the overhead, the burden of the hardware interrupt itself. So for demonstration of these optimizations, we've implemented an I/O path on the left side with an HAL, which is essentially architecturally similar to the SCSI layer, the conventional SCSI layer on the right. And the HAL has an extended interface which has a fine-grained interface powerful than the original SCSI mid-layer in API. It has some active operations to check the device status and so on. And our optimizations were implemented at an IO strategy layer as a block device driver, which exploits the extended HAL IP calls introduced. And the purpose of these HAL calls is to provide fine-grained access to necessary context, which is the hardware interrupt context itself, the user space the user space context, and so on. Details are discussed in the paper. Okay, so for evaluation, we've employed 6 Samsung SATA 3.0 SSDs connected on a single Intel Z87 chipset. It's running on AHCI. The workload was parallel direct I/O random reads with 128 threads. It's really parallel, and we varied the block size of the random reads. The lines are the measured IOPS, and the bars indicate the bandwidth of each measurement. And our optimizations were compared to the conventional SCSI-based I/O implemented in Linux 3.2.40. Compared to the normal SCSI I/O stack, our optimized path shows significant IOPS gain when the block size is smaller and when the parallelism is much higher. And the performance of the original SCSI I/O path was limited somewhere around 330 IOPS. These SSDs support like one device support about 110K IOPS. This only measures about like 3. On the other hand, there wasn't any gain, no special gain with larger IOs, and this was mainly because we were capped by the DMI 2.0 uplink to the CPU, which supports only about 1.5 gigabytes measured bandwidth, and since it's the request size were quite large. Next is the result of an evaluation with a key value storage called Aerospike 2. And this key value storage is able to use multiple SSD as a key value storage backend. And we also use the same 6 SSDs for this evaluation and measure the throughput of the operation when we load the system with YCSB, increasing the client parallelism. And at the highest throughput, which was about 115K ops per sec, the gain over using the original I/O stack was about 7%, while at the highest load, the gain increased up to 100%. And this shows the benefits of reducing the number of context switches under higher parallelism. And so far we've shown techniques required to optimize the I/O path for current generations of flash SSDs. And we found that previous I/O path optimization techniques, which are proposed with next generation NVM technologies, were not quite sufficient. There were like multiple context switches in the completion path, which was introduced to enhance system responsiveness and system throughput. However, they were causing unbounded, unpredictable delays when processing I/O and showed limited performance. And we managed to minimize the number of context switches without sacrificing the very system responsiveness and throughput, and showed that the reduction of context switches is effective in enhancing system IOPS, especially under highly parallel workloads. And I think this is pretty much about it. Thank you for listening. I'm ready to take any questions.
I'll take a quick question. So this is impressive engineering work. One might, however, sort of has the concern that by consolidating those I/O contexts, you're breaking the modular structure in the kernel coding.
Yes.
Does this sort of make the kernel code less manageable, or that's a wrong sort of takeaway from this?
Well, I think that these kinds of interkernel optimizations make the kernel developers freak out, but these companies which actually sell these kind of things, the high-speed SSDs, really want to squeeze out these performance out of the I/O stack, so they usually go with like customized I/O paths. So our work was somewhere in the context of like vertical optimized I/O stack. So yes, it kind of breaks the manageability or those kind of stuff, but still, I think it's manageable, fairly enough. Yes.
Just a quick comment. Some of this refactoring, in particular, putting a little more work into the ends and into the hardware interrupt routine and eliminating the soft interrupt, is actually a step back to where things were 30 years ago, when the trade-offs between the speeds of the storage and the speeds of the machines were quite different. So this isn't meant to judge it good or bad. It's just interesting to see how the pendulum swings back and forth.
See, but well, I quite wonder because these days we have multiple cores, and the effort was like trying to spread the load. The intercontext itself is kind of serialized, and by doing this, the one benefit of this was expanding the parallelism of the. And this really matches how SSDs works. So it has a lot of parallelism inside, and we actually have to use it to squeeze out performance out of it. So,
but I think it all gets driven from the trade-offs between the speeds of the different pieces, and how big a fraction of how significant the overhead is, for example, to generate the soft interrupt, and then to switch context again from there. And so the way I see it, it's partly driven just by the ever-shifting trade-offs between the pieces of the overall system. And so it's not surprising that we revisit some of the answers we used before, because some of the questions have shifted to desire those answers again. And it'll shift another way in the future.
okay.